Okay, welcome. We'll get started in just a little bit here. A reminder, if you could keep your video cameras off so I don't get a whole bunch of boxes, I'd appreciate it. And again, you could do that through the participants next to your name. Just click the little camera guy and make sure it's off. And again, we'll start in just a few minutes here. Give everybody an opportunity to kind of come in. Again, we'll get started in just a few minutes. Again, reminder, if you keep the videos off and all that, so not getting any boxes all over the place and stuff. Yeah, we'll talk about the pre-lab in just 1 second. Just give me a second here to get everything going. All right, hang on 1 second. Try that. Again, if you need to turn your video off in the participants, you should be able to click your video off. Let's see if I can get this to share with you. There, I think. All right. There we go. All right. That, and let's see that. All right. All right, you should hopefully be able to see the screen, I hope, as well. And again, a reminder as we go through, if you do have questions, type it up there in the chat box is probably a good idea. And I'll be able to read it and answer your question. So let's see here. Stuff we were scribbling on last time. So if you do have a question, ask it through there. So question was about the pre-lab for experiment 15. That is That is the next experiment, if I'm not mistaken, I think, right? That's the flame test. Is that correct? Okay, so in terms of the labs, we'll just talk about it up front here. We'll also talk about it towards the end as well. But since we are taking the exam next week on Monday, we're essentially going to, if you look at your lab schedule, we're going to just move all the labs back one day. So as of now, I haven't had a chance to change the pre-lab setting on Cengage, but I will later today, hopefully change it. And I know it says it's due on the 30th because that's originally when we're scheduled to take it and do that experiment. So since we had the postponement here and kind of getting everything together, I'm going to move it back. So scheduled for next week was flame test on Monday, and then I believe I think it was on Monday was the flame test, and then on Wednesday was the next experiment, which was the lead to iodide precipitation experiment. So what you're going to do is just basically move all your experiments back one day, and then that would move the next experiment after the flame test, which was the lead to iodide, to the following Monday, and that would move the gas experiment from that Monday to the Wednesday, where we did not have a experiment scheduled. So in terms of the pre-labs, I'm going to move them in accordance. Next week, we will take the tests on Monday, and we'll talk a little bit more about that towards the end of class here today, or lecture here today. So you'll take the test during the lab time like normal, and then we'll just move the experiments forward one day. That means I do need to go and adjust all of the pre-labs for that. I haven't done that yet, so give me at least a day or so to kind of adjust all those things. In terms of the online homework, I believe I moved it. If I did not, I will move it past Monday, I think I might have already did it. I'll double check though the online homework, but I will double check that as well. Any other questions on any of that type stuff? Yeah, so in short, there's no new lab today. So technically scheduled for today was, if we were still in person, we would have took the exam today during lab. So I'm just gonna keep today lab period as no lab. I will start a lab session, even if there's one scheduled, and it'll just pretty much just be open if you want to ask any questions or anything like that. Since we do have, I guess, an exam coming up, you could ask some questions on that material. But then on Monday, you'll take the exam. That will free up the time for lab, during lab time, for you to take the exam, or at least start it during that period of time. And then we'll move the flame test to Wednesday of next week, which I think puts us into April. And then the experiment that was scheduled for next Wednesday, which is the lead to iodide, which is kind of what we have on the screen actually, will be started the following Monday. And then the gas experiment, which I think was magnesium, for that week will be moved to the Wednesday where there was no experiment essentially. So if you look at the schedule starting next week on Monday, just move all the experiments forward a day. And then you'll eventually run into a day where we did not have an experiment scheduled, and it'll all just sort of lock into place. Any questions on that? Okay, I thought I did move the homework, so that sounds about right. So I think I already did the homework to the 31st, which is the day technically after the exam. And then, like I said, I haven't had an opportunity to do so, so I will move the pre-lab questions or pre-lab assignments to their appropriate day when we'll do those experiments. Any other questions on the lab part or anything like that? And like I said, we'll take some time at the end of lecture here to discuss the exam and how it will work on Monday and what we'll be doing on Monday. All right, so let us continue on lecturing so we don't use so much time about all this class stuff, hopefully. So we sort of finished talking about a type of reaction, which is really, as I mentioned last time, a double displacement reaction. And in a double displacement reaction, The way you could recognize it again is by really what you see on the reactant side. You will see two ionic compounds. So a positive guy and a negative guy on one, and a positive negative guy on the other. And essentially what will happen is the two positive guys will basically switch places. So the two positive guys will switch places. As I totally missed that turn off there. Let's go that way. So two positive guys will basically switch places. So we'll get two new ionic compounds. We'll get A and D that will come together. And we'll make basically C and B that will also come together to make another ionic compound on this side. And oftentimes these type of reactions are also what are known as precipitation reactions. And basically what a precipitation is, and again, sometimes a precipitate is abbreviated PPT. It's basically what we got right here. So the result of these guys switching partners and making new ions and new compounds, one of these guys on the product side, based on some solubility rules that we'll talk about, will make something that's a solid. Probably not both, but one of them usually will become a solid. And that solid is what is known as a precipitate. And that's why these type of reactions are oftentimes called a precipitation reaction. So that experiment that we're going to move from next Wednesday to the following Monday is that type of reaction. And that is actually what is made in that experiment that you'll see. Obviously, as a video, I imagine at this point, is that lead to iodide. And that's what we see here. The lead is positively charged, as we see. The nitrate is negatively charged. Our sodium is positively charged. Our iodine is also negatively charged. So essentially what happened to make our products, again, is these two guys basically switch partners. Now, we talked about some different types of reactions to illustrate what's going on. And what we see written up here on top, let's grab a different color real quick. What we see over here on top, where we write everything together in their correct formulas, that is again sometimes what is referred to as the molecular equation. But in solution, as we talked about, because these guys are ions, those guys, when they are in solution, they will essentially break apart into their ions. And we could write another equation like what we see up here. And I think we did last time at the very end there, this equation here, where we break apart everything into their ions. The only things that we don't typically break apart when we do this type of equation are really three things. Anything that is a solid will stay together. So that's why when we got to this part, the solid stays together. Anything that is a liquid would also stay together. So if you had something like water involved, it would also stay together. And the third thing that I don't know if we'll come across a lot in this class, but you will maybe in the next class, things that are weak electrolytes. So we talked about weak electrolytes. Weak electrolytes, something, for example, like hydrofluoric acid. When it is in solution, it pretty much stays together. It does break apart a little bit into ions, but mainly stays together and won't break apart into a lot of ions. So this type of equation that we have up here, as we talked about last time, this equation is what is known as the total ionic equation. And when we write the total ionic equation, we could always find some ions, or usually could find some ions on both sides of the arrow that essentially look exactly the same. So in the above one that we finished last time, if we look, we have NO3 minus on the left-hand side. We also have NO3 minus on the right-hand side. We also have the two sodiums on the left-hand side. We also have our two sodiums there on the right-hand side. And as it says here on the handout, these are what are referred to as our spectator ions. Yeah. And they're on both sides, obviously, here as well. And that's how you could recognize something as a spectator ion. You could basically see the ions in the exact same form on both sides. And if you correctly balance the equation and you correctly distributed the coefficients and such when you come back into here, those spectator ions should completely cancel out on both sides. So if you ever write a total ionic equation and you see like spectator ions on both sides, but they don't completely cancel out, probably in most cases what that means is either you have the wrong formula, you didn't distribute the coefficient correctly, because they really should cancel out completely, those spectator ions. And when we do cancel out those spectator ions, because basically what a spectator ion is, as the name implies, it's just kind of hanging out watching what's happening. It's really not part of making the product of that particular reaction. We typically will cancel out those spectator ions like we talked about last time. And when we cancel out that spectator ions or those spectator ions, what we are left with is another type of reaction, our equation, which is known as the net ionic equation. And our net ionic equation, as we can see down here on the left, is a result of taking our spectator ions and essentially canceling them out. And what that leaves you is what is truly happening in this reaction. So really what is truly happening in this reaction is the formation of this solid. And that's why this is oftentimes called a precipitation reaction, because we made that solid that is formed. And basically, although we mix together all of these things in the solution form, and in that solution we had all of those ions here floating around, the real reaction is taking place is really only when the lead ion and the iodide ion come together to form our solid that we get here. So that's the third type of equation that was very commonly written for this type of reaction, which is known as the net ionic equation. It kind of gets rid of everything really not involved in the reaction. It kind of cuts it down to the bare minimum of this is truly the reaction that you're observing. So again, this is truly a double displacement reaction, and really double displacement, sort of if you want to think about it, is a big category of types of reactions. And one type of reaction that you could put underneath a double displacement is a precipitation reaction. Another one that we will see in just a second, I think, is an acid-base reaction. It's another type of double displacement reaction, and we'll look at some examples of that in this chapter as well. But sort of the big category of types of reactions is double displacement, and within that category, there's also some types of descriptions like precipitation reactions, acid-base reactions, that kind of fall underneath that category. So as we talked about last time, there's oftentimes many different ways you could classify the same reaction. It just sort of depends on what aspect you're looking at in terms of what you're trying to sort of classify. But again, most people would call this a precipitation reaction, but it is also, again, a double displacement reaction. Any questions on that? So a good question would be like, how do we know if we put some things together, we're going to get basically a precipitate that forms? And what helps us decide whether or not, when we put two ions together, for example, will that combination give us a solid or will it not give us a solid? And will they be soluble in each other? So there's certain solubility rules, which we'll see on the next couple pages here. And these solubility rules really help us determine whether or not something will make a solid when they come together or if they won't. And it's really broken up into sort of three categories. And most of the time we really deal with oftentimes these two here. So if you look at solubility rules or a solubility table, much like you had in one of those earlier experiments, and it says that these things would be soluble. What that essentially means is it should get the aqueous symbol written next to it. And basically what that means is you have a solution. When you mix those two things together, or those two solutions together, those ions, when they do come together, should basically be a solution. You shouldn't see any type of solid formed or anything like that. Now, on the other hand, if you look at the solubility rules and it says it's insoluble, what that means is that guy should get a solid symbol next to its formula, which indicates pretty much that when you put those two things together, you would expect some type of solid to form. So for example, in the last one that we looked at, when we put together the lead with a +2 charge, and it came together with our iodide with a -1 charge to make that PbI2. The combination, when these two guys pretty much get together, based on solubility rules, tells us that a solid would be made. It's insoluble, and that's why that formula there had the solid next to it. And it's based on these solubility rules, which we'll see in the next couple of slides here. Now, the third classification, which again in this class may not come across too often, is slightly soluble. And for the most people, think about slightly soluble as still technically being insoluble, but it does mean exactly sort of what the name implies. A little bit of it will dissolve, but for the most part, most of it will still remain as a solid. So if we do come across something that's slightly soluble, probably for our purposes here and most purposes in chemistry classes that you take, you probably could consider it as being insoluble. But again, a little bit of it will sort of dissolve. And in real life and in real sort of applications, even things that are technically insoluble under certain sort of parameters, you can get it to sort of be soluble. So, you know, in general, when we talk about soluble and insoluble, we talk about basically the idea that in water, will it dissolve or make a solid? There really is no sort of symbol for slightly soluble. I guess on some tables you may see SS written next to something, like in a box for in terms of solubility, and that would be slightly soluble. But like I said, in most cases, most people would consider the slightly soluble to be more like insoluble. So if you were to use it probably in a actual chemical equation where you're writing the formula and want to do the symbol, you probably would put S next to it for solid. But in like a solubility table, and again, perhaps if you remember, we had that earlier experiment in the post lab where it was kind of like a table like this. There's a bunch of, say, positive ions on this side, a bunch of negative ions on this side, and there was a bunch of boxes. And in those boxes, it maybe said S, it maybe said I. And that's typically, again, what a solubility table looks like. You find the two ions, move your fingers to the box, and see what it says. If it says S, it means it's soluble. If it says I, it means it's insoluble. So probably Grace, that would be probably the only place you would probably see like SS written in a solubility table, and just to indicate that it is slightly soluble. But typically in an equation that you write, you wouldn't write SS next to it or anything like that. So you would either choose AQ for aqueous or S for solid. And again, if it was slightly soluble, probably the solid would be more of the symbol that you would use. So let's take a look at some of these solubility rules to help us decide. So what we're looking at here on the screen are things that are typically soluble in water at 25 degrees. And again, this is just some of the rules here, but pretty much everybody in group 1 is going to be soluble, which means as soon as you see any formula that contains an element in group 1 on the periodic table, it's pretty much a safe bet that is going to be soluble, which means all those guys will get that aqueous symbol next to it. Same thing when you see ammonium. Anything that has ammonium in it will definitely be soluble all the time, and it will be aqueous. Things that contain nitrate, chlorate, and perchlorate are also soluble, so those guys would get the aqueous symbol. Now, there are certain things that are normally soluble. So the first main one that you oftentimes will come across is the next one. And the next one here says basically if you take chlorides, bromides, or iodides, these guys are normally soluble. But unlike the previous ones that we just talked about, there actually are some exceptions to their normal solubility. And for these guys, there's basically 3 exceptions. When we look at it here, it is exceptions are silver, that's mercury 1, and that is lead 2, which means when you come across an exception for the solubility rules, it means basically the opposite occurs. So if you have chloride, bromide, or iodine in a formula, and it does not contain silver, mercury 1, or lead 2, it means it will get the aqueous symbol here. But if you have chloride, bromide, or iodide connected with any of those 3 things, silver, mercury 1, or lead, it becomes the opposite and it becomes insoluble, which means it would get the solid symbol next to it. So there are some things that are soluble in, 90% of the time, but there are some exceptions which would make them go from being soluble to insoluble. And that's why if we think about the one that we were just looking at when we looked at the PbI2, when we look at the PbI2, when we look at the solubility rules here, we see I, which tells us it is iodide, soluble in everything except for silver, mercury 1, and lead. And in this particular case, it's attached to lead 2. So it would go from soluble to insoluble. And that's how we know when we put the lead with a +2 charge together with that iodide that we would expect a solid to form. Now, in addition, sulfates are typically soluble in everything except for calcium and silver, which are slightly soluble. So again, those would probably lean a little bit towards the insoluble side. And barium, mercury 2, and lead sulfate, which are insoluble. So again, there are some sulfates here that have some exceptions to the normal solubility. Any questions on things that are soluble? So everybody on the screen typically should be soluble, should get the AQ symbol, except if it's one of those exceptions, then the opposite would happen and it would become a solid. So let's take a look at some of the rules for things that are typically insoluble. So typically things that are insoluble are going to be our hydroxides. Hydroxides are typically insoluble, but there are some exceptions. So typically they're insoluble, which would mean that they would get the solid symbol. But because there are some exceptions, and the exceptions are the alkali metals, barium, and calcium. Alkali metals is basically group 1. And if you remember from the previous slide, everybody in group 1 is soluble in everything. There's no exception. So that includes hydroxide. So what that means is if we have something like sodium hydroxide, hydroxide normally being insoluble, but because in this case it is connected to a group 1 ion, it would make it soluble, and this would be aqueous in that case. So again, there are some of those sort of exceptions that mean the opposite. Carbonates, phosphates, and sulfides are typically insoluble in normal cases. So all these guys over here, again, should get a solid next to it, except if it happens to be connected to one of these 2 guys. And these 2 guys, again, are what we saw on the previous slide. These are group 1, which is soluble in everything. And then also it is ammonium, which again is NH4+, which is soluble also in everything with no exception. So if you see something that contains carbonate, which is CO3, phosphate, which is PO4, and sulfide, which is S, they most likely and 90% of the time will be soluble, the exception being obviously somebody that contains group 1 or ammonium. Any question on things that are typically insoluble? Yeah, so if there is a group 1 available in the in the compound, you pretty much don't have to look any further at anything else. You pretty much could go, it's going to be soluble 100% of the time, because there's really no exceptions for group 1, just like there's no exceptions really for NH4+, and there's no exceptions really for NO3-. So as soon as you see those things, you really don't have to worry about what else is in there, because there's no exceptions. You know that it's going to be soluble. Other questions on that? So for example, if we take a couple of things that I think we mixed before, and I don't click the wrong button there, let's try that again. If we take a couple of things that we've sort of mixed before, if we take, say, sodium chloride plus silver nitrate, and again, this is a double displacement reaction, positive, negative, positive, negative. My sodium is going to go hook up with my nitrate on the other side. So that's sodium, which is +1, with my nitrate, which is -1. So they'll come together. The silver will come together with the chloride, silver being +1 and the chloride being -1. So they'll come together with that formula right there, with our silver chloride. So we could use our solubility rules to figure out each of these things, you know, are they going to be soluble? Are they going to be insoluble? So starting over here, maybe I'll change the color here real quick. So starting over here, we look at this, and as was the question just a second ago, as soon as I really see sodium, I'm pretty much done. I don't have to worry about anything else. I know for sure it is going to be aqueous. You can also, in this case, look at the chloride, because there is some solubility rules about the chloride. And if you look on the previous page, when we look at chloride, they are soluble in everything except for silver, lead, and mercury 1. And in this case, the chloride is attached to sodium, so that will also tell you that it's soluble. But in this case, as soon as you see that sodium, you're pretty much done. You don't have to worry about it. When we look at the silver nitrate, we may not be able to find silver by itself on that table, but we can find nitrate. And again, if you look at nitrate in terms of the solubility rules, is pretty much soluble in everything with no exception. So that's pretty much all you have to worry about. And that also should get a aqueous symbol next to it. Now, coming to the other side, again, when we look at the sodium nitrate, we hit sodium, that's group 1. Again, we're pretty much done at that point. We don't have to worry about it. We could go right to it being aqueous. But just in case you want to double check, you could also find on those solubility rules nitrate, which is also soluble in everything, which again will tell you the exact same thing. So in certain cases, you can actually find information about both ions on the solubility table. And in certain cases, you may just be able to find information about one of them. But in those cases, the information you find about one of them is probably enough to figure out whether or not it will be soluble or insoluble. Now, when we get to the end there, we have silver chloride. Again, here we could probably find on the table the chloride. And the chloride, again, is soluble in everything, but there are 3 sort of exceptions. And the 3 exceptions are silver, lead, and mercury. And in this particular case, as you can see, we do have silver. So this is going to be an exception to the normal sort of solubility rules. So instead of normally like it is soluble, it's going to become insoluble. And it will get a solid here. And we will make this sort of white solid when you mix those 2 solutions together. And you will make this white solid, and that will be the sodium chloride. Any questions on how to go through and use the solubility table to figure that out? As I mentioned before, this is a double displacement reaction, but because our solubility rules also tell us that we do make a solid here, this is also referred to as a precipitation reaction as well, because we did make a precipitate, obviously the silver chloride. And just to tie it together with what we've been talking about in terms of the different types of equations, The first one that we have up here would be the molecular equation. And it is balanced, so I think it's balanced. If we broke this up into our ionic equation, or our total ionic equation, again, we would want to break up everything that's aqueous and leave together everything that is solid. So the sodium chloride would break apart into a sodium ion plus a chloride ion. The silver nitrate would break apart into a silver ion plus a nitrate ion. Now, when we come to the other side, our sodium nitrate, which is aqueous, will also break apart into a sodium ion and a nitrate ion. And lastly, when we get over here to our silver chloride, as we talked about, when we get to the total ionic equation, anything that's a solid, anything that's a liquid stays together. So in this case, our silver chloride would be written together here and not broken apart. And again, this would represent our total ionic equation, the equation that shows pretty much how everything is in that particular solution. And it is this equation where we would find our spectator ions. So if you look at it, you should hopefully again be able to see our spectator ion here is sodium on both sides. And we also see again nitrate on both sides as our spectator ions, right? And as we talked about before, we typically will cross those out on each side. And that will leave us the next type of equation that we talked about. What you're left with is the silver with a +1 charge coming together with the chloride with a -1 charge to form silver chloride that has a solid. And this equation here is truly the reaction that is taking place when you mix those two solutions of sodium chloride and silver nitrate. And this represents that third type of equation that we talked about, the net ionic equation. Any questions on how to use the solubility rules, how to write those equations? So the question is, why did I put the silver before the chloride? Truthfully, in the equation part, which I think you're talking about there, and perhaps in the net ionic equation, it really doesn't matter, I guess, in terms of on that side of the arrow. But the normal way that we typically do things with ions is usually the positive guy comes first and then the negative. So that's usually how we write it in the formulas. And usually most people will kind of keep that sort of trend going here when we sort of write equations as well. They're typically put the positive ions first and then the negatives, just sort of a normal way that it's sort of done. Other questions on this, or how to use solubility rules? Now, in terms of the solubility rules, you should be familiar with them. They probably will be provided for you if you do need them. They'll probably be provided for you, probably like that table that you saw in that experiment we did earlier on in the semester, where basically you just kind of, and I kind of drew on the other page, I think. Right, where did I draw that guy there? There you go. So they'll probably be provided for you, much like that experiment, and then something like this, where basically you find the two ions, and again, just move your fingers to the box, and if you see in that box it is S, it means it's soluble and should get the aqueous symbol, or if in that box you see the I, it should also get the solid symbol next to it. So that's probably how they'll be provided for you. You should, again, be somewhat familiar with some of the common ones. Again, things like chloride, bromide, and iodide come up a lot. Nitrate, ammonium, and group 1 guys, they come up a lot. So at some point as you keep using it, you'll probably have those guys almost memorized, but for an exam or anything like that, they would be provided for you. Other questions on solubility? So the next type of reaction we're going to talk about is acid-base reaction. And again, for the most part, these are going to be what are known as acid-base neutralization reactions. And again, pretty much they also, for the most part, can be placed under the double displacement kind of big banner of type of reaction. So they're also typically, especially when you mix for example, a strong acid and strong base together, it usually will be that a kind of double displacement reaction that's taking place. The difference between sort of these reactions and the precipitation reactions is with an acid-base reaction, we typically don't get a solid that's formed. We oftentimes will make water as a product. And just a little bit about acids. Acids have sour taste. So obviously don't taste any acids if you're in the lab again. Colors, they do cause litmus paper to change color. So litmus paper, just a little paper. I think we might use some of it for an experiment. But if it goes from blue to red, it typically means it's acidic. They will react with metals to produce hydrogen gas, and you've done some of those, I think, in person. It's those bubbles that you see when you put a piece of metal like magnesium in hydrochloric acid. You'll see some bubbles being made, and that's the hydrogen gas that's being generated. And if you have a strong acid, for example, it's typically a strong electrolyte, which means it does conduct electricity and does completely break apart. Bases, on the other hand, they have a bitter taste, also don't taste anything. They feel slippery. A lot of soaps, drain cleaners, those type of things, those are all bases. You could even, I think, go to Home Depot and buy like almost straight sodium hydroxide to kind of clear your plumbing drains and stuff like that instead of Drano and stuff like that. They also change color. In terms of litmus paper, typically if you use litmus paper and it turns blue, that usually means basic. And also we can have strong bases as well that are good conductors of electricity and strong electrolytes. We could also have weak acids and weak bases that are weak electrolytes as well. So when we look at an acid, really what an acid is an acid is really something that will be able to produce H+ ions in solution. So if you remember when we were talking about sort of nomenclature and acids, pretty much the cation for all acids is H+. And so for example, HCl, which is hydrochloric acid, again, typically will have that aqueous symbol in it, is basically made up of H+ ions, which is our cation, and our Cl-, which is our anion. Yeah? And that's basically what makes something an acid, is having that H+, because when it is in solution, it pretty much will break apart and produce free H+. And that's essentially what the definition of an acid is the ability to produce in a solution a free amount of H+ that's floating around. Sometimes H+ is referred to as a proton, and it's referred to as a proton because if you remember, hydrogen has one proton, one electron, and no neutrons. So in order to become positively charged, it has to lose an electron, which pretty much just leaves it a proton, which is why, especially in acid-base chemistry, H+ is sometimes referred to as being a proton in that particular case. So if we do have strong acids, and we should know these names since we talk about nomenclature, there's no oxygen there, so that's our hydrochloric acid. This has oxygen, that's nitrate, which becomes nitric acid. And that is sulfate with oxygen there, which becomes sulfuric acid. Yeah. So these guys are all strong acids, and there's a certain amount of strong acids, and those are three common ones. So things like HCl is a strong acid, nitric acid like we got up there, sulfuric acid is another strong acid, perchloric acid is a strong acid, Hydrobromic acid is a strong acid. Hydriodic acid is also a strong acid. So these are some very common strong acids that you sometimes will come across. And yeah, so the question was, what makes it an H plus? Remember, when something becomes positively charged, it becomes positively charged because it lost an electron. So in order for the H to become H plus, it would have to lose an electron so that it has more protons than electrons. And since hydrogen only has one electron, that's why it becomes positively charged, N plus one. So when you have any of these strong acids, what that essentially means is when it is in solution, you don't have any of those units still together. So they're all strong electrolytes like we talked about, I think, the other day. And that basically means that, again, if you have your hydrochloric acid, when it's in solution or you have a solution of hydrochloric acid, you basically have 100% H pluses floating around and 100% Cl minuses floating around. You no longer have any of the HCl units still together in that particular solution. And that's really why something like hydrochloric acid or even nitric acid, as well as you can see on the screen, in solution, they pretty much generate a ton of free H plus. And because they generate a ton of free H plus at once, they're considered a strong acid. And that's something different than, say, a weak acid, which we might touch upon here as well. But a weak acid will pretty much stay together, produce a little bit of free H plus, which is why it's still considered an acid, but nowhere to the extent of these acids here. They will pretty much be 100% broken apart into their ions. Bases, on the other hand, work the same way. Now, bases work pretty much the exact same way. Yeah, so the question is, when it says virtually every molecule becomes an ion, that is the case. So in solution, if you have any of those strong acid solutions, or even, as we'll talk about here on this page, a strong base, what that means is that, again, they're strong electrolytes. And if you remember when we talked about electrolytes, I think the other day, a strong electrolyte pretty much means when it's in solution, it 100% broke apart into ions. And that means that you have absolutely none of those kind of whole units together. So in the case of something like hydrochloric acid, you have no HCl units still together. They're all in solution as H plus ions floating around freely. They're all Cl minuses floating around freely. So again, if you had like a beaker of hydrochloric acid solution, what you would have in that beaker is a bunch of H pluses floating around freely, a bunch of Cl minuses floating around freely. You would not have any of those HCl units still together in a strong acid like hydrochloric acid. So it would just be those ions floating around. Now, bases are things that typically produce hydroxides in solution. And hydroxide, a reminder, is that polyatomic ion, which is OH minus. So anything that has the ability in solution to produce hydroxide is considered a base. Now, a lot of strong bases are strong electrolytes, and a lot of strong bases, much like what we see down here, have actually OH minus in the actual solution or the formula to begin with. By the way, that's a typo. I don't know if it's corrected on your paper or not, but that should obviously be a plus down there. So if we look at something like sodium hydroxide in solution, just like our strong acids, 100% of what you got floating around is going to be those ions. So again, same idea. If you have that sodium hydroxide in solution, 100% of what you got floating around are those ions. Again, you will not find any of those sodium hydroxide units basically still together. And something like sodium hydroxide is a strong base. Something like potassium hydroxide is also a strong base. And if you think about the periodic table, for example, sodium, potassium, things like calcium, they're found in group 1 and group 2 on the periodic table. And if you remember, group 1 is our alkali metals. Group 2, right, is our alkaline earth metals. And pretty much what the word alkaline means, it means basic. Yeah? So if somebody says something is alkaline, what it means is it's basic. And essentially, most of our strong bases come right here in group 1 and 2 on the periodic table. So a lot of our strong bases will have, drop that down there. That is where we'll typically find most of our strong bases. And usually our strong bases will have the hydroxide or OH minus in the actual formula. Now, some bases don't actually have hydroxide in the formula, but they're able to produce hydroxide. Very common example of something that's a weak base. So very different. A weak base is a weak electrolyte. And a weak electrolyte, unlike a strong electrolyte, this guy mainly stays together. But does produce a few ions. So when we take something like NH3, and when it's in water, what it will actually produce is NH4 plus and OH minus. So when something like ammonia, which is NH3, is in water, it is able to produce hydroxide. So it is still considered a base. But as we talked about, these arrows here indicate that it's a weak electrolyte, and that is why it is considered a weak base. Because in order for NH3, for example, to produce hydroxide, it pretty much got to go find some water to do that. Unlike these guys, like our sodium hydroxide and our potassium hydroxide, in order for those guys to produce hydroxide, they essentially just need to go in for a swim. So as soon as they go in for a swim, they're going to break apart into those ions. If you have something like ammonia, it's still able to produce hydroxide, not as much as these guys, because this guy over here is going to produce a lot of hydroxide very, very fast. Ammonia needs to kind of do a little reaction to produce hydroxide. So it's still considered a base, and it's a weak base because it can still technically produce a little bit of hydroxide, but it is nowhere near as strong as something like sodium hydroxide or potassium hydroxide. Any questions on that? So when we do take a strong acid and a strong base together, this type of reaction, again, is something that's referred to usually as a acid-base neutralization reaction. And the overall sort of generic reaction that occurs is when you take a strong base and a strong acid together, you basically will produce two things. You will produce water, and you will produce what is referred to as a salt. Now, basically, the water is going to come from the H plus from the acid and the OH minus from the base. So that's essentially where our water will be generated from. The salt is really just an ionic compound, which means basically you have a positive, negative guy together. All reactions of strong acids and strong bases, regardless of what combination of strong acids and strong bases that you put together, the overall net ionic equation that you get is essentially the formation of water. and that is when the H plus comes together with the OH minus. And again, the H plus comes from the acid, the OH minus will come from the base, and we will make water. Is always the net ionic equation that you get when you do a strong acid and a strong base together. And that would be following sort of our total ionic equation, net ionic equation, like we talked about. So for example, if we look at a reaction between hydrochloric acid, which again is a strong acid, and so again, this is our strong acid and our strong base. And we could write, this is our molecular equation. We can break these guys up into our total ionic equation. So because HCl is a strong acid, it will 100% break apart into H plus ions plus chloride ions. Same thing with our sodium hydroxide, which is a strong base. It will break apart into sodium ions and hydroxide ions. Now, a little bit different than our precipitation reactions, here we form water, which is a liquid. And if you remember, when we do our total ionic equation, we keep together anything that's a solid and a liquid and a weak electrolyte. So in this case, we would not break apart the water because it is a liquid. The sodium chloride, on the other hand, would break apart into its ions. And this would represent our total ionic equation. And just like we did previously, we can look on both sides of that equation and we could find some ions that look exactly the same. And in this particular case, we will see that we have Cl minus on both sides, again, looking exactly the same. We have sodium on both sides, looking exactly the same. And these guys would be our spectator ions. And just like we did previously, we would cancel those guys out on both sides. And what that's going to leave us, as what we saw on the previous page, is ultimately what is happening when you take a strong acid and a strong base together is the H plus from the acid will combine with the OH minus from the base. And those two guys, when they come together, want to make water. And this is what our net ionic equation will look like. So this, again, no matter what combination of strong acid or strong base that you put together, and if you go through the molecular equation, the total ionic equation, and the net ionic equation, they will all pretty much end up in the exact same place, which is the formation of water. And that's why the formation of water is sort of a driving force for a chemical reaction to take place. Just like a solid being formed is a driving force for a reaction to take place. And when we do look up here, again, with our strong acid and strong base, we do produce the same two things that we talked about. We produce water. And in this particular case, in the molecular equation here, this is what is referred to as our salt, which again is just an ionic compound. Any questions on that there? In addition, if we truly look at this reaction, like I mentioned before, if we take the original things that we started with, essentially, what we have here is that double displacement reaction. This is our positive guy. This is our negative guy. This is our positive guy. This is our negative guy. So this is not a precipitation reaction because we did not form a precipitate, but this is still could be classified as a double displacement reaction because essentially the H plus comes together with our OH minus and our sodium comes together with our chloride to form our guys. So this reaction is probably best classified as a acid-base neutralization reaction. And that's why it's sometimes called the neutralization reaction, because ultimately what you're doing is producing water. So because you're producing water, it's referred to as being neutralized and a neutralization reaction. But it also could be sort of broadly classified as a double displacement reaction, because also what's happening is essentially our two positive ions are switching partners. Any questions on any of that there? Okay. There's a bunch of stuff underneath it, which is all of the stuff I already wrote on the screen. So I'm just going to kind of go through it. Here's a couple of other sort of examples. Again, the top one is the one that we were just looking at. Here's nitric acid and potassium hydroxide. And again, that's a strong acid and a strong base coming together. And if you went through all the steps that we just did on the previous one for this reaction, you will also end up in the exact same spot for your total ionic equation. Again, in that last one here, it's basically the H plus from the nitric acid coming together with the OH minus from the potassium hydroxide. And ultimately, that's what you're going to end up with in terms of your net ionic equation, is basically that formation of water. In this case, in the first one, the sodium chloride on the right-hand side is our salt. So that's our salt. And for our second one, the potassium nitrate is also our salt. So in most cases, I would say in most cases when you react an acid and base, especially a strong acid and a strong base, for the most part, that salt is going to be soluble. It is potentially possible that you could create a salt that is a solid, but I would probably say in most cases, probably 98% of the time, your salt is going to be something that's going to be aqueous or soluble in each other. Any questions on acid-base reactions, which are really, again, double displacement reactions? Okay. So that sort of classifies really, again, the big category here of double displacement. And within that sort of double displacement reactions, as I mentioned earlier, we have our precipitation reactions and also our acid-base neutralization. So what we're going to talk about now and sort of moving on in the next little bunch of types of reactions is sort of the next big classification of reactions. And these are what are sometimes referred to as redox reactions. And redox reactions means oxidation and reduction reactions. So that's essentially what redox basically means. And this, again, is sort of a big classification of different types of reactions. And as we go through it, we'll see some other classifications or ways you can classify reactions. But ultimately, when we talk about oxidation and reduction, oxidation basically is a result when something loses electrons. And reduction is a result when somebody gains electrons. So for most general chemistry sort of applications, when we talk about oxidation and reduction, we're really looking at the idea of gaining and losing electrons. There's some other definitions of oxidation and reduction which involve oxygen and hydrogen. More so in organic chemistry, you kind of get into those, so we won't get into too much about that. We may see it in just a second. But sometimes people will remember that one of two ways. Sometimes we'll remember Leo the lion goes grr. So loss of electrons, oxidation, gaining of electrons, reduction. Some people are fond of the oil rig. Oxidizing is losing, reducing is gaining. So there's a couple different ways that sometimes people remember what is being oxidized, what is being reduced. You can put them together. Leo the lion, that's on an oil rig and he goes grr. You don't have to choose or anything like that. But there's also sometimes an easier way or more of a visual way that sometimes you could figure out oxidation and reduction. And I sort of think about it like this, as sort of a basic number line. So to the right of our number line is positive numbers of 0. To the left are negative numbers. So if you remember, just basically, if somebody loses electrons, they are going to become more positive, right? Because they have more protons than electrons. And vice versa, if something gains electrons, they are going to become more negative. And that's because they gained electrons. So you literally can use the number line, and if you move from one side to the next, so for example, if you move in this direction, things are becoming more positive. That indicates that an oxidation occurred. While if you move in the opposite direction, things are becoming more negative. That means that reduction is occurring. So this is usually a very simple sort of way to do it. You could go, okay, the thing started with a +4 charge, ended with a +2 charge. I'm moving to the left. So that's going to be a reduction, or vice versa. It started with a -1 charge, which would be, over on this side, and moving towards a 0 charge, which would go to the right, which means an oxidation is occurring. So sometimes that number line is kind of very helpful to figure out whether or not something is gaining electrons or losing electrons. Any questions on that? All right, so let's take a look at some of this here. So if we look at this reaction here, where we have basically the formation of sodium chloride, just a reminder that if you do have something like sodium metal by itself and it's not combined with anything, it pretty much has no charge. Yeah. Remember that things only get charges when a metal and a non-metal come together. So if you take any of those metals off the periodic table, they're uncombined, they're by themselves, they will have no charge. If you look at something like Cl2, also, that is naturally how chlorine comes as a diatomic molecule. It also has no charge associated with it. These two things really don't get charges until they come on the other side and actually come together. And in this form, the sodium has a +1 charge and the Cl has a -1 charge. And again, they don't get those charges until they come together. So if we think about our little number line sort of guy that we did on the previous page, we can use it to determine sort of what is happening with each of these guys. So let's take a look here. If we take, for example, the sodium to begin with. So the sodium here is going from 0 to +1. So literally you can do the purple, starting at 0, +1 would be going in this direction. And we see we're going to the right here. So we know that the sodium is going through oxidation, becoming more positive. You could also do the same thing for our chlorine. So you could start with its initial charge. And if we look at our chlorine here, it is starting at 0, which would be here. And it is ending up over here at -1, which means it's essentially moving in this direction. And we can see moving in this direction here is reduction. So the chlorine is actually going through reduction in this particular case. Any questions on that, how to figure that out? So this is a type of reaction which is really a redox reaction. Switch back to maybe a better color there with the blue background. And this again is a redox reaction because basically we have a transfer of electrons. And a transfer of electrons is also sort of a driving force for a chemical reaction to take place. And that's essentially what's happening here. This type of reaction is also, as we'll see a little bit later on as well, but since we have it up here, this also can be called what is known as a synthesis or combination reaction. And basically, as we'll see in a synthesis or combination reaction, you essentially take two things and you make one thing. So we took two things and we basically produce one thing. And that implies that this is a synthesis reaction, which you can classify it as, but you could also classify it again in sort of the broad, big way as a redox reaction. So this one, most often, probably if you had to classify it in a chemistry class, it probably would be classified as a synthesis or combination, much like the experiment that you guys did on Monday. You saw the video for that type of reaction. But sort of the big classification of where that synthesis reaction would fall under is still a redox reaction because we have a transfer of electrons. Any questions on that there? So here's another example. Oops, back here. And another example is magnesium oxide formation, which I think was part of that experiment that you saw. And same thing here. If we look down here, magnesium by itself has no charge. The oxygen is naturally how it comes. It has no charge. Again, when they get on this side, that's when the magnesium's can get a +2 charge. That's when the oxygen's going to get a -2 charge. And again, if you look at your number line, when we look at the magnesium, it's starting at 0. And it is ending at +2, which means it's going to the right. And that means it's going through oxidation. And if we look at the oxygen is starting at 0 and ending at -2, which is going to the left. And that means it is going through reduction. And that's what's represented here. These are what are sometimes referred to as half reactions. And these guys are half reactions where we indicate the oxidation and reduction reaction. So this guy, which is our oxidation reaction, and this is sometimes referred to as the oxidation half reaction. The way we could recognize it as an oxidation half reaction is we see the electrons on the product side. So since we see the electrons on the product side, that indicates that those electrons are being lost or given away. And that will typically indicate an oxidation. The opposite is a reduction half reaction. And the way you can recognize that is the opposite is true. You will find the electrons on the reactant side in a oxidation half reaction. Not a lot of times they do form solids, these type of reactions. A lot of redox reactions are single replacement reactions, for example, which we'll talk about as well. So a lot of them do make solids, like that magnesium oxide, for example. A lot of times this is what happens, for example, you plate a metal on another metal, so you kind of uh, put those metals on there. Or we perhaps did an experiment earlier on where you put some metals in some solutions, and maybe you saw some stuff sort of form on the metal and stuff like that. Those are all sort of redox reactions when you saw those type of reactions occur. They don't always have to form a solid. So for example, if you think back to the experiment we did with the halogens in the fume hood, where we had the different layers, those are also redox reactions, but you really didn't form any solids in that case. You just had the liquids and stuff like that. So a lot of times they will form solids, but they don't always have to necessarily form a solid. Other questions? We could also do that for this guy up here. So this is the one we were just talking about. So if we were to write the oxidation half-reaction for the guy up here, we would start with our sodium, that's solid. Since it's oxidation, it will go to sodium with a +1 charge. And we would lose that electron. While if we did our reduction half-reaction for this guy up here, we would start with our Cl, and it would gain an electron, and it would make our Cl minus. Truthfully, to balance it out, this would have the chlorine. You would have 2 here, which would give you 2 electrons as well. Let's go through there, and then we'll have our balanced one. So to truly balance it, you would also need 2 of those. So kind of balance everything, you technically would have 2s on all of those guys. But those would be our half reactions. Here we have our electrons on the reactant side, which indicates reduction. Here our electrons would be on the product side. So this type of reaction, which is again called a combination reaction, also known as a redox reaction, here again is our balanced one for our magnesium oxide, which we went through. Again, product side for oxidation, reduction reactant side for our reduction. Now, I did mention a little bit about sort of oxygen and a couple other definitions of oxidation and reduction. And technically, oxygen just has to be involved, but 2 other definitions of oxidation and reduction. And again, in our class, we really won't get into too much of these definitions, but a definition of oxidation, another definition in addition to electrons, which you can use electrons most of the time, is that if it gains oxygen from the reactant side to the product side, or if it loses hydrogen as you go from the reactant side to the product side, and reduction would be the opposite there. Another definition would be that if it lost oxygen going from reactant side of the equation to the product side, and if it gained hydrogen going from the reactant side of the equation to the product side. So those are 2 other definitions of oxidation and reduction. And again, really organic chemistry, you come across a lot of that because it's much easier to look at hydrogen and oxygen organic molecules because there's not a lot of metals involved. But in general chemistry, there's a lot of metals involved, which means you can sort of figure it out based on the metals. So for example, down here, if we were to kind of follow those definitions, when we look at the sulfur on the left-hand side, it has 2 oxygens. When we look at the sulfur on the right-hand side, it basically has 3 oxygens. So going from left to right, the sulfur gained electrons. So the sulfur gained, not electrons, I'm sorry, sulfur gained oxygen, which means that the sulfur is going through oxidation. And as silly as it may sound, the oxygen on the left-hand side went from being by itself to nothing. So it actually lost oxygen. So the oxygen by default would be the thing going through reduction in this case. By the way, those things do go together always. So if there is something that gets oxidized, there is something that gets reduced. So those things are always tied together. So if something gets reduced, there should be something getting oxidized, and vice versa. They always go together. And the nice thing about that, because they always go together, is if you could just figure out one, you'll know what happens to both of them. So for example, if you can figure out what is being oxidized, you will be able to figure out what is being reduced in that case, and vice versa. So for example, in this down here, we were able to figure out that the sulfur was being oxidized, and that's all I needed to know. So by default, the O2 there would have to be the thing that's going through reduction. Any questions on that? Okay, so I think we're getting towards the end of lecture here. So let us talk about a couple things that's going on. So we're getting towards the end of this chapter, so we hope we should be able to finish it. The plan for next week is, we'll start with today. So again, as soon as we're done here, I'll take a little break and I will start the lab session. Again, you do not have a lab today. So in terms of lab, let me see here. Something I can scribble on, I'll just scribble on here maybe. So in terms of lab, let me do this actually. Don't screw up the next slide. Hang on one sec. Maybe. There it is. So let's just put a new slide in there. There we go. All right. Then let's pop that back up. All right, let's try that again. Pop that back up. Hopefully, there we go. So in terms of what's going on in terms of lab and everything, in just a second here. So for lab, so for today, again, will just be review questions. If you have any of those type of things. On Monday, that's when probably the exam one will be scheduled. So you could go and use that time to take the exam. On Wednesday, we're going to move the flame test from Monday of next week to that Wednesday. So I believe this is 3:30. So then that should be April 1st, if I'm not mistaken, hopefully. And then the following Monday should be, I forget what the true title is, but it says something like lead 2 iodide. So that would be, was that one? 6, give or take, yeah. And then to Wednesday, where we did not normally have a lab scheduled, which I guess would be the 8th. And again, if I'm off by a day or so, I apologize. That experiment will be the gas one that was originally scheduled. So just starting on your lab schedule, just kind of move everybody up one day, essentially. And again, I'll try to do it today sometime, but if not tomorrow, the latest, I will adjust all the pre-labs for these to correspond to these dates. That will give us some time to sort of hopefully catch up on some of this stuff and allow you to do those things. In terms of Monday, this coming Monday, which is 3:30, we will have lecture at our normal time. So just to kind of get through some of the stuff that maybe, try to keep on pace, because we lost a little bit of time kind of catching up this week and stuff like that. So like normal, like we normally do, I'll probably lecture a little short on Monday. So we won't go probably the whole time. And then like I said, afterwards, that should free you up, hopefully, to at least take your exam. Any questions first on the scheduling before I talk about the actual exam in just a second? Okay, so in terms of the actual exam, this is my plan at the moment. And like I said, before Monday, I'll send you an announcement. But the exam one, or actually, it's not exam one, whatever exam we're on, two, I think, perhaps, right? So exam two will happen Monday, and it will be done through Canvas. So you'll need to log into Canvas, and you'll be able to take the exam. You know, it'll be kind of posted like as a quiz, but it'll pretty much be an exam, right? And like I said, I will send out more detailed announcement. I don't know if I could get to you by Friday, but definitely before Monday comes. So make sure you check, you know, the rest of the week and through the weekend, your Canvas and your email for any type of detailed announcement that will come. So a couple of things. The test obviously will have a time limit, and we'll adjust for anybody that needs it adjusted through your accommodations through DSPS, if you should have any of those. What that means is when you start the quiz or the exam, when you start the exam, you will get a clock and a timer. And once you start it, the timer will not stop, or it cannot be paused or anything like that. So before you start the exam, you want to make sure that you are completely prepared to take the exam. You want to make sure that you have obviously your calculator. You're going to need some paper, because you will need to upload, much like your assignments for lab, a file that shows your work. So there will be some problems where you do need to show work, and I still want you to work those out on a piece of paper, and you will have a certain amount of time, you know, after your exam's done to upload that work with it. And that's because, as you know, it's all done on the computer. So if I don't have work, it's like all or nothing. So if you put the wrong answer in, you're not going to obviously get points for it and stuff like that. So my goal is that even if you put the wrong answer or got the wrong answer, if you upload your work for those problems that do have work associated with it, I at least can look at your work and be able to assign you some partial credit. Yeah, so again, as soon as you start it, my understanding is the clock goes, and there's no like, I want to start just to take a look and come back type thing. And it's really for that reason. So you can't like preview the exam and then go find all the answers and then take the exam. So once you start it, the clock goes. It cannot be paused or restarted or anything like that. Okay, so that's why I'm saying you want to make sure that you're really prepared before you begin it. Okay, so make sure you have a calculator. Make sure you have paper that you're going to have to show the work, again, for problems that have work associated with it. When you do show the work, make sure that the questions are clearly numbered so I know exactly what it is. Yeah, so it's a very good question. So since this exam is about drawing Lewis structures and stuff like that, I anticipate that as part of your sort of show your work paper, you might, and I think the easiest thing would be to probably have you draw those Lewis structures on your paper at home and then upload it, okay? But there will be questions associated with the Lewis structures, like, you know, what is the molecular geometry? What is, you know, is it polar, non-polar? You know, those type of things that you will be able to enter into the computer. So I don't think there's going to be a way, and I'm still kind of working on it, but I don't think there's going to be a way you're going to be able to actually draw something like a Lewis structure. So in the question, what it will probably say is, on your paper, draw the Lewis structure for this compound. And then there will be additional questions probably next to it that you can answer up on the computer as to things like, what is the molecular geometry? What is the, you know, is it polar or non-polar, and those type of things. So I know for sure probably at this point, the Lewis structure part, you're going to have to draw the actual structure on the paper, okay? A couple of things about your scratch paper, not really scratch paper, but the paper where you'll show your work, is it does need to match the answer. Honestly, I haven't written yet, Mark. I'm not really sure. So it will probably be similar to a normal exam that we take. So in terms of the questions, it will be similar to a normal exam. The type of questions will be similar as well, but they probably will be some type of, I don't want to say true multiple choice questions, but it may be some multiple choice questions. It may be like fill in the blank type questions. And that's just a way I could get you to enter the answers in online, where you would normally just kind of write it. And there may even be like a short answer type question where you can just type something in that type of question. So it'll probably be a variety of questions. I'm going to try my best to make it very similar to like the exams we've taken in person together, and kind of put it together in a sort of as best of a similar format as of what we've done in class. Okay. Now, in terms of the work that you need to show, you need to show the work for any problems that have work associated with it. So what I'm also going to do is, as you read the questions, you will be able to, it will say on the actual question, you need to show work for this question, okay? And there may be some questions where it will say you do not need to show work, which obviously means you don't have to show work for those, okay? I'll talk about time limit in just a second, okay? In terms of that, so I'm going to try to, in each individual question that you answer, kind of have a little title at the beginning that says, you need to show work for this one, and ones where it says you don't need to show work for it. So you'll clearly know which ones you should show work for and which ones you don't have to show work for. In terms of the work, it should match the answer that you submit online. So for every single question that's on the test, you do need to submit an answer online, and the work that you upload in that file should match the answer that's there. You cannot just say, I'm just going to answer everything on the scratch paper. If you do that, I won't grade it. So you do need to enter the answer online, and then you also need to show the work. The work is like normal. You need to show anything that has units, setup, sig figs, all that stuff. And it's again for your benefit, so I don't have to make it like all or nothing. So if I see you missed the answer or something like that, I have an opportunity to look at your work and try to give you some partial credit. Yeah, I think I'm going to try to make everything as in terms of clarification, I'm going to try to make everything as clear as possible, since we will be meeting for lecture for a little bit, and then afterwards, what I might do, I'm not sure what the best move would be for that. Either maybe I'll open up a meeting, and then if you have some questions, you could ask me during that meeting, or you could email me during that meeting in terms of questions. But my hope is everything should be pretty self-explanatory in terms of what you need to do and what you need to answer. Just like a normal exam, I will provide any type of conversions that you need. I will provide any type of conversions that you need. So formulas, again, you do need to know. So things like your polyatomic ions, your geometries and all that type of stuff will not be provided for you like normal. You do need to know those things. Now, in terms of answering the question and entering the question on the computer, here's the deal. There will be specific information about how to enter those answers. And this is also why uploading your file with your work is important, because again, I will go through everything and make sure that, it wasn't marked wrong because of some type of entry thing that the computer didn't like, and I'll have your work and your answer to sort of show that. So for answering online, what I'll say, Grace, in terms of that, for answering online, in terms of sig figs and all that, follow the actual instructions for each problem as to how to enter the problem. So for example, if it says enter it with 4 decimal places, enter it that way, or if it says enter with the correct number of sig figs, do it that way. There will be instructions on each question on how to do that. And again, when I get your work and kind of go through it, I'll be able to see what you put in. I'll obviously know the right answer. So any type of adjustments that needs to be made, I'm going to try to do that. I would appreciate if you kind of put all the work into one file. Again, you can kind of scan it in using maybe that Adobe Scan app. But make sure, again, that your work is labeled in terms of the problems. So I don't have to hunt it down. Try to be as clear as you can so I don't miss something. Because again, this is all electronic and kind of different for me as well. So I don't want to miss anything. I will provide those conversions, any type of conversion factors. And what I think I'll do is, again, I'll probably maybe stick them in each problem so that you can see them in each problem. You don't have to go hunt them down. In terms of a periodic table, obviously I will provide you a periodic table. I'm trying to figure out the best way to do that. The periodic table may just be posted separately where you can maybe take it and print it out so you have it to use during the exam, but any type of conversions and stuff like that. With that being said, it is still an exam. You're still expected to do it like normal with honesty and all that good stuff. Yes, you're supposed to do it with closed notes and no notes and kind of do it like you would in class. With that expect, we have the timer, so hopefully that will discourage you from trying to do all that. We'll talk about what chapters are in just a second. You will have a regular amount of time, so we'll start it around lab time as to when you can take it. I probably will add a little bit of extra time. I know it's a little bit different for everybody to take it online, but probably not a tremendous amount of time, so you won't have like all day to take it, you know. So you will have that time limit that will start and not stop, and you'll have an opportunity to take that exam that way. Also, just a reminder, some of it is computer generated, which means don't have the wrong answer, the right answers on the wrong version. Again, you will have probably unique questions for most of the questions. So just keep that in mind before you decide to do something that you shouldn't. Again, if anything is found out that you sort of violate doing it by yourself, it's not you doing it. You kind of worked with other people. Obviously, normal rules apply. That is still considered cheating and results in a 0. Yes, so hopefully we won't have any of those type of issues. So once you complete the exam, also a very important thing is make sure you actually hit the submit button. Yeah, don't hit it too soon that you submit without answering all the questions. But once you've completed the online version, which you do have to again put an answer for every question, make sure you actually submit it. Once you've done with that, you then should go, because I will know what time you actually submitted it. You should then go and upload your work file within a timely fashion to do so, so that I can have that file and check everything out. Any other questions on that? So again, just a reminder that the exam will cover the original chapters that it was before we went on spring break, which off the top of my head, I'm not sure, Grace, if it's those chapters, but I'll just say I believe it should be the chapter in terms of nomenclature. It should also be the chapter in terms of Lewis structures. I want to say it's the chapter with, I believe it's the chapter with empirical molecular formulas, if I'm not mistaken. And that would be obviously, I think, moles and all that kind of stuff. And I feel like I'm missing one chapter. I want to say it's, I want to say it has to do with phase changes in energy, perhaps. So whatever it says on the syllabus for that exam, those chapters is still going to be only on those chapters. So obviously nothing that we've talked about since coming back here. And I think before spring break, we finished on chapter 6, which is not on this exam either. So no balancing of equations or anything like that. To be honest with you, Mark, I'm still working out what I think after I write the exam. I'll sort of think about the time limit. You would obviously have at least, you know, an hour and a half to 2 hours, would be my guess. And again, after I'm done writing it, I'll sort of figure out what I think is appropriate to give you the correct amount of time for taking the exam like normal, and maybe just a little bit extra time because again, it is online and you have to kind of write those stuff down and stuff like that. So again, I have to try to find a sort of a good balance between the appropriate amount of time and not like a crazy amount of time to do it and stuff like that. So right now I would say at least I would imagine you would have probably at least 2 hours to do it. And again, as soon as I'm done writing it, I'll sort of evaluate the exam and see if, how much more time you might need for that. Other questions about the exam or anything like that that's happening? So again, a reminder that we will still lecture like we normally do. Again, we'll cut it probably short on Monday so you could kind of get set up and prepared to take the exam. And then for the lab time, which you should hopefully be available for, it seems like you'll be able to kind of knock it out during that time and upload your file. And then the following Wednesday, we'll just continue lecturing like normal. And then the flame test will be the experiment. Any other questions in terms of what's happening? And again, like I said, definitely for the rest of the week, and obviously in the future as well, for the rest of the week for sure before Monday, make sure you continuously check the Canvas site and the email associated with it, because I do anticipate sending out sort of a more detailed announcement in terms of the exam and sort of where you could find it, what you need to do, and sort of those rules sort of apply for that. Any other questions on any of that? So for today's lab portion, again, since there's really not a lab for today, that reminds you, looks like the time might have passed, but hopefully you submitted your lab from Monday to me. But for today's lab session, again, I'm just going to leave it open. And if you have questions, since we do have an exam coming up on Monday, it's been a little while since we've talked about those things. I'll just be there almost like, like an office hour if you want. You could pop in if you want or pop out, and you could ask a question if you have something in regards to maybe the exam material, even the stuff we're talking about now if you want, but I imagine most of you, maybe if you focus on the exam part. Other questions on anything? A reminder again, all these recordings can be found on our Canvas site in the module section. And again, it takes a little bit of time to kind of get it processed and uploaded. But again, you can watch it through Canvas. You can watch it through Canvas and either through YouTube as well. It's a good question about attendance. So I think what I'm going to do when I started doing some of my other classes is maybe towards the end of the week, I'm going to put up some type of quiz or survey on Canvas. It won't really count for any points or anything like that, but it'll just be maybe 2 or 3 sort of quick questions that you could just go up on Canvas and sort of answer, and that will be just a way to kind of check in and kind of do attendance that way. So towards the end of the week, you might see something that pops up on Canvas that's just kind of like a survey quiz. It's not the exam. It's just sort of a quick way to kind of keep check of attendance and stuff like that. So again, just in case you can't make a lecture and watching the recorded ones, I'm probably going to do that every week towards maybe Friday or something like that. Again, I'll just put like a short little, 2-3 question type of survey. Are you able to maybe, access everything okay? Those type of questions. Nothing really chemistry too related or anything like that, but more class related, where you could just kind of fill out the survey, and then I kind of could use that for like, okay, you're still participating in the class and stuff like that. So that's a good question. So probably Friday, look for one of those kind of surveys to pop up. And again, you do just want to go on there and do it, and that will sort of count for attendance for this last week. Other questions? Okay, so since we ran a little long talking about all that, what I'm going to do is I'm going to personally take a 10-minute break to kind of stand and stretch and all that. And I'll start the separate lab lecture. We'll go about 12:25. We'll start it. And again, in terms of today's, it's really just going to be more, I'll be there if you have questions about, anything in terms of maybe the exam or any topics that we're talking about. I'll be more than happy to answer those questions. Other than that, I'll either see you in lab, or again, I'll see you on Monday, our normal time, for a small, short lecture before you go take the exam. Other than that, have a good one. I'm going to end, I think, this current meeting. Thank you, you too. And I'll see some of you maybe in lab in about 10 minutes or so. Just give me a few minutes to kind of stretch. All right. Have a good one, everybody. If you're out for the weekend, have a nice weekend and all that good stuff too.